All right, hello everyone, welcome back. We're at our 7th lecture of the quarter. So today I will continue talking about electric fields and forces and voltages and potential energies. I kind of briefly introduced it last week. We're gonna go into slightly more details as you've already started doing in DL this week. Okay. So this is pretty much where I left off last week. So what we looked at is point charges. So here's our source point charge, which is here at the center. And then we thought about the voltage that it generates and how that's related to potential energy that some other charge, when there's another charge present, how that's related to the potential energy associated due to the interaction of the two charges. So before we get into introducing what we call test charges, let's just review these equipotential lines, which express to us the voltage which is generated in space. So basically what these lines represent are values of voltage in space that are present because of this positive charge being present. So there's a value of voltage everywhere in space. It's continuous, but we can't write down a number everywhere in space. So we choose this representation of equipotential lines, which show us regions where the voltage is the same. So this circle represents, so we choose this value 4 volts here, it's kind of arbitrary, and everywhere along the circle the voltage is 4 volts. It also, the way we represent equipotential lines is that neighboring lines are always incremented by the same amount of voltage. So we go from 4, so the increment we happen to choose here is 1 volt. It doesn't have to be. We could have gone from 4 to 3.5 to 3, but here I'm just showing an increment of 1 voltage. So the difference between these two is 1 volt, difference between this two is 1 volt, these two is 1 volt, and so on. Now, what the distance here represents, because this is in physical space, what it's showing us is how rapidly that voltage is changing as you go away from that positive charge. And I don't have that equation represented here, but we found last time that it goes as 1 over R, which tells us that the voltage decreases at a slower rate when we go farther away. So that's why here you to have that same change in voltage, you have to go a larger value of R. So these circles get farther and farther apart. Now, so that's what gives us a voltage. And now what we can do is we can put a positive charge in here and think about, in terms of voltage and potential energy, which way does it feel a force? So we already know that opposite charges attract and like charges will repel. So kind of just by having this information, we know that the force will be away from the other positive charge. But pretend we didn't know this, and we're just using kind of these concepts that we have developed. So what this equation tells us, it connects the voltage of the source to the potential energy change of some test charge Q. So because voltage due to the source is decreasing away from the positive charge, what that tells us is that because Q is positive, our test here is positive, that the potential energy will also decrease away from the charge. And because this equation gives us that connection between force and potential energy, and we know way back from 7A days that force will point in the direction of decreasing potential energy. So what that tells us is then the force will point in that direction. Now, if we put a negative test charge here, this delta V doesn't change because that's source dependent. So we know that delta V decreases in away from the charge, so in that direction. But because Q now, our test is negative, what that tells us, it flips the sign of which way delta P is decreasing. So if delta V is decreasing away, delta P is going to decrease because of this negative sign in front towards. So the negative charge's potential energy will decrease towards a positive charge, and due to this connection of force and potential energy, we know that force points towards. And again, using our knowledge of opposite charges attracting, that makes sense that the force should point in that direction. So I also want you to notice another thing that's shown in this diagram. The arrow that I drew here for this positive charge is longer than the arrow I drew here for the negative charge. So going back, thinking back to our vectors, the length of error represented the magnitude of the vector. So what I'm saying is that the force over here is bigger than the force over here. So why is that true? Well, if we look at this equation, what this equation tells us is that the minus sign kind of tells us about direction, but this is the slope. So what this is telling you is how fast the rate of change of potential energy. And that's, of course, related to the rate of change of voltage. So if your voltage is changing rapidly, meaning that you don't have to go too far to have a delta V, then that tells us that this slope is large. So that tells us that the magnitude of the force has to be large as well. So when we're closer to the charge, these equipotential lines are closer together. That closeness tells you about the rate of change. So you could think about the density of the equipotential lines is related to the rate of change of voltage, which is then related to the magnitude of force. So the closer you are, the stronger is the force. And we again know that from a couple of DLs ago when we discussed the fact that this electrostatic force decreases as you move away from the charge. So if you're farther away here, you have a shorter error because the force is weaker here. The density of equipotential lines is smaller. So this kind of discussion gives us sort of a general result that positive charges seek lower potential. So we have a positive charge and it wants to go where it wants to decrease its potential energy, and its decrease in potential energy will point towards decreasing potentials, where negative charges will seek higher voltages, because when delta V is increasing with a Q negative, that's when delta change in potential energy is decreasing. So that's going to be the direction of the force. So it's reversed with positive and negative. As we'll see, everything will be when we talk about this material. All right. So one thing that seems to be kind of missing, let's actually go back a little bit. So we have this connection between potential energy. So we have something that this voltage, which we define as source dependent, and then we have something called potential energy, which we say depends kind of on the source and the test, the interaction between the two. Now force here, which is a vector, that's something that depends on the interaction again between the test and the source. So it seems like we could come up with kind of an analogous thing to voltage, but that's a vector quantity. So that's what we're gonna do next. So force, again, it points in the direction of decreasing potential energy. So we know that, and that's the equation. So let's define a new quantity, which we call an electric field. It's a vector. We use capital E to represent it with a vector sign over it. And it points now in the direction of decreasing, not potential energy, but decreasing voltage. So you could see that these two equations are very similar, except now we're talking about voltage was something that depended on the source. Potential energy depended on both. Force depends on both. So electric field, kind of by analogy, we see should depend just on the source. So the same way potential energy and voltage was related this way by multiplying it by the test charge, that's exact same relationship between force and electric field. They're both vectors, so they're just multiplied. You just multiply the electric field by the scalar Q to get the force. So here, everything on the right side of these two equations is something that depends on source, except voltage is scalar, electric field is vector. And then on the left side, what this explains is either the change in potential energy or the force that a test charge feels due to that, to the sources. All right. Also, we want to actually define, so what we're going to do first is we'll go back, think about the force, how we define the force between point charges, and then from that, we'll split that up in terms of source and test and electric field. All right, so going a little bit back and thinking about from last lecture and last week, the definition that we saw for potential energy, and then using this relationship between force and potential energy, all you have to do here is take the derivative, and then the minus sign from the derivative will cancel, so we get this expression for the force. But remember, this, just taking the derivative just talks about magnitude, but force is a vector, and this little r hat represents the direction of the force, and that force is, it's radial, which means it goes away from the point charge. So this is, again, depending on what's interacting, you might get different forces. This is specifically a force between 2 point charges, where Q1 is the charge of the first charge and Q2 is the charge of second charge. So we see that if they're opposite, so if one is positive, one is negative, we get this minus sign. So that means that it's, instead of going away, it's going towards, so it's attractive. If they're both the same sign, whether it's two positives or two negatives, you get a positive F, so it's radial away, which means repulsive. So this is actually a very famous and familiar equation, a very common equation in physics known as the Coulomb's law. And here's a picture of Coulomb. Kind of resembles Napoleon a little bit. I guess it's just the time period. It's French from the 18th century. All right, and don't worry too much about these constants yet. I will have a slide later on sort of discussing it, but K is just a constant. Q's have units of coulombs and R's unit of meters for distance. So to get, in order to get force to work out to be newtons. Okay, so now that we know the expression of force between 2 point charges, let's think about it in terms of a test and a source charge. So there are 2 charges involved. So let's think about what is the force on charge Q2 do or by Q1. So this on by notation is going to be important to us when distinguishing the field or the source versus the test. Okay, so here's our full expression. So what we say here is then, because we know that force is equal to the charge times the electric field. So what this force equals to is, because we called Q2 our test, so it's Q2 times the electric field generated by charge Q1. And now if we look at this equation and just pull out the terms, which is the electric field. So again, source is our Q1. It generates an electric field everywhere in space, the same way it generates a voltage everywhere in space. And then charge Q2 feels that field. So the electric field here is just going to be KQ1 over R squared. So instead of over R, like for voltages, for forces and field and electric fields, we're going to get 1 over R squared relationship. And then the test charge, again, Q2 feels this electric, feels an electric force in the presence of that electric field. So then you just take your electric field and multiply it by Q2. So we kind of go back to our initial equation. So this is how we're going to look at we're going to separate the idea of field versus force. Okay, here I just want you to quickly practice using this equation and think about kind of the meaning of the two charges. So here it's just written as little q, big Q, just because this is how these charges are indicated, but that's equivalent of saying Q1 versus Q2. So what I have here is two charges interacting that have different values of charge and also different separations. So I'm asking you to look at these different charges and separations and decide which pair represents the strongest force, or in which case. So here I'm asking you the large Q, because that's the one that's staying fixed everywhere, feels the biggest force. All right, pause the lecture, think about this. It's just basically using this equation. All right, so actually let me go back a step. So we know that as R increases, here the force is going to get weaker. So for these larger R's, so we have the same values of Q like here. So if you compare B and E, B is clearly going to be weaker because it's a larger R. If you compare D and A is going to be weaker. Again, same Q's, larger R. So now let's compare these two versus, so these two, here we have a larger 2Q, so there would be a larger value here in the numerator, which means that D has to be larger than E. So now we're kind of left between C and E. So at first it doesn't seem very obvious, because here what we have is half the distance, but also half the total charge. So basically it all comes down to thinking about what has a larger role, the Q or the R. But because the R is squared, R is more significant. So the one with a shorter distance should win. So if we actually work this out, you know, you see here, obviously all of these are smaller. Here we have a bigger numerator, 2Q, little q, big Q, but it's just over R squared. Here we had a bigger a smaller numerator, Q times little q times big Q, but we divided by R over 2 squared. That became R squared over 4. The 4 goes up. So you see actually the force here is double than the force here. So the idea here is just to get an intuition about this force. The separation plays a bigger role than the actual value of charge. All right. Okay, so now we're gonna, again, kind of take a step back. So what we did before in the slide that looked very similar at the beginning of this lecture is I looked at this equipotential lines, then I connected that to potential energy and potential energy to force. But for now, we're gonna just forget about force because we're only worried about having one source charge. We don't care about test charges yet. Electric field is something that's source dependent. So you don't need a test charge to figure out which way the electric field will point. And then this equation, which relates voltage now with electric field, tells us that electric field decreases in the, electric field points in the direction of decreasing voltage. So for positive source charge, voltage decreases away from the charge, so that tells us that the electric field also points in that direction away. Now, another thing that's important to incorporate when you're drawing your electric field vectors is magnitude. And magnitude is related to the rate of change of voltage. So we've already discussed this, that the higher the density of these equipotential lines is, that tells us that this dV/dr is largest there, because again, there's a smaller delta R for the same delta V. So the bigger this delta R, delta V over delta R will be a smaller number. So right here, you have to go a much larger delta R to have that same delta V. Low density means the slope is smaller there of your potential energy as a function of this, or your voltage is a function of distance, which implies that the electric field is weaker. So as you go farther away, these arrows should get shorter. So it's longest like over here, kind of medium somewhere over here, and even shorter out here. So what I've shown you here again is just a randomly selected locations to show the electric field vector. But this electric field exists everywhere in space. So again, we're gonna, the same way that we came up with this representation for equipotential lines, we're gonna come up with a representation for electric field vectors. You know, how many do you choose to show? Where do you choose them to show? And so on. So this is where we introduce the idea of field lines. So you should have seen that already a bit in DL. So the way it works is, you know, you have some space, this area that you're interested in representing your electric field, and you have a bunch of field vectors as you see here. So what we do is we draw these field lines in such a way that they're kind of tangent to these electric field vectors. You got to be careful. Electric field lines are not the same as electric field vectors. They're just a representation. So another thing is that you can do then, once you have, because what's physical is the electric field vector. So you have a bunch of, you know, let's say you've represented your electric field with electric field lines, and then you want to go back and think about, well, what are the electric field vectors there? So there's two pieces of information. First of all, electric field lines are always going to be tangent to, or vectors are going to be tangent to the lines. But then how do you decide whether, you know, choosing 2 points in space, like if we go back here, magnitude also played a role. We knew here, because we saw the equipotential lines that over here had a stronger electric field compared to over here. How do we know that from these lines? Well, that's related to the density of the electric field vectors lines. So when they're more dense, I'm mixing up those words in my head, but yeah, lines and vectors are different. So when the field lines are very dense, that tells us that electric field vectors are larger there, larger magnitude. So if we wanted to draw now a bunch of vectors in various places, first we choose a point there, that's going to be kind of the Taylor vector, and then you draw a tangent to the field line, and also we see where it's more dense, these vectors should be longer, larger magnitude here compared over here where the field lines are less dense. So again, these field lines are just a nicer way to represent your field vectors. So if we go to our point charge, you saw previously that, you know, I just drew these 3 electric field vectors. We saw that they pointed away from the charge. We also saw that they were larger magnitude, closer to the charge compared to away. So if we look at these now electric field lines representing, just make sure that it's consistent. So if you choose any point along the field line, the vector will be tangent, which means because it's just a straight line, just parallel to it. So always away from the positive charge, because remember, electric field points in the direction of decreasing voltage. And also this density tells us about the magnitude. So you see that over here close to the charge, the field lines are more dense. There are more field lines per unit area compared to out here. They get more spread out, smaller electric field, a smaller magnitude of electric field. So this is how the field lines look at for positive test charge, and we see that kind of the general rule is going to be that the field lines will start at the positive charge and go away from the positive charge. The opposite is true, and I believe I have a slide, yes, for negative charge. So for negative charge, if you recall, I think I had the equipotential for negative charge last lecture. The voltage increases towards the charge. So we have, you know, -1 here, -2. No, sorry, it decreases towards the charge, increases away from the charge. So opposite of what it was for positive charge. So you see, as you go away from the negative charge, it's getting less and less negative until it gets to 0. So it is increasing away from the negative charge, decreasing towards a negative charge, and because the field has to point in the direction of decreasing voltage, the field lines will end at positive charges. So they always point, sorry, negative charges. So the field lines or electric field vectors will always point towards the negative charge, or we can say that electric field lines end at negative charges. All right, so I've been talking a lot. Let's actually apply some of these ideas to a couple of questions. Think about this. So this is going back mostly to connecting electric field with voltage and then thinking about potential energy. So what we have here is an electric field, which is represented by these black arrows, all pointing to the right. So you have these electric field lines. And then we put in this negative, that's what Q minus less than 0 means. It just means it's negative, test charge somewhere here. And now what you want to do is you want to move this test charge to these different locations, 1, 2, 3, 4, and 5. And you want to figure out, when you make that change, or you change the location of that charge, which change results in the biggest increase in potential energy. So think about how basically this electric field is related to potential energy. So as we know, we've now introduced these 4 concepts. We have voltage, we have potential energy, we have electric field vector and force vector, and all 4 of them are connected somehow. So you can often reason, let's say, knowing electric field, you will know something about voltage and potential energy, or knowing voltage, then you can make conclusions about electric fields and forces. All right. So let's see the answer. So it turns out to be either 4 and 5. So there's perhaps different ways of answering this. So the way I chose to represent this is first to think about in terms of voltage. So we have these electric field lines which are parallel. What does that tell us? It tells us that the density of electric field lines, like over here versus over here, is the same. If the density is the same, it means that the magnitude is the same. So what it's telling us is that the rate of change of voltage is constant. So how do we represent that? By drawing equipotential lines, which I chose to draw them dashed here just to make them different from the field lines, not to get them confused. By the way, when you will often see pictures where you have equipotential lines and electric field lines in one picture. So the way you distinguish them typically is the electric field lines have arrows because they have a direction associated with them, where voltage is a scalar, so they wouldn't have arrows. Here I also made it a dashed line, but it doesn't have to be. Often it is just a solid line. So because, again, there's no change in density of electric field strength is constant, that tells us that the rate is constant, so they're going to be equally spaced. That's kind of a side note. It's not, and will come up again later. It's not necessarily essential to answering this particular question, but just to explain why I drew these dashed lines equally spaced. But to answer this question, what was really mostly important is to use this equation. So we want to figure out about the biggest increase. So we want to see where delta P is increasing. To do that, we have to figure out where delta V is increasing. Which way is delta V, or actually where delta V is decreasing because the Q is negative. Now this equation tells us that electric field points in the direction of decreasing voltage. So that means that the voltage has to decrease in that direction, going to the right, because that's the direction the electric field is pointing. So, and you see that with these numbers, arbitrary numbers I chose. So I chose this equipotential to be 4 volts, 3, 2, 1, 0. So it's decreasing in that direction, which means that the potential energy will increase in that direction. Why? Again, because our test charge is negative. Q is negative, so the sign of delta V will be reversed from the sign of delta P. So that means the potential energy will increase towards the right. So kind of 3, 2, and 1 are out. Now 4 and 5 are equivalent because we see that they lie along the same equipotential line. So another rule that maybe I haven't mentioned is that equipotential lines in electric fields have to be always perpendicular to each other. And the main reason is because we know that field has to point in the direction of decreasing voltage, and along an equipotential line, voltage is not decreasing or increasing, it's staying constant. So it means that the field has to point perpendicular. It cannot have any component along the direction where it's constant, because it has to point in a direction where it's changing. So they're always perpendicular. So that means because these are parallel, the equipotential line is just going to run straight up. So everywhere vertically, if we choose any 2 points that are vertical from each other, they're going to have the same voltage. So it doesn't matter if you move your charge up here or down here or just straight to the right, you're going to have the same change in potential energy. So this might remind you a little bit of gravitational potential energy, where it just depended on height. So if you're holding a ball and if you moved it straight up by 1 meter, or if you did a bunch of things with it or just went at an angle, but if the net change was 1 meter higher, the path didn't matter. All it mattered is how much the height changed. So kind of similar here, it doesn't matter if you go straight to the right or up, you have that same change in voltage, so the same change in potential energy. All right, so here it's a little bit more challenging, I think, because you have to, they're no longer parallel. So you have to think here a little bit what these different shapes represent. So what we have here are 3 scenarios or 3 sets of electric field lines. They're all 3 are pointing to the left. And another thing you're told is there are these 2 points, A and B, and they're the same distance apart. There are no test charges involved here, just field lines and voltage. So here I say electric potential, it's just another way of saying voltage. So the question is, which shows the biggest change in electric potential when you move from A to B? So think about this. And again, this equation should help you with that. All right, so let's take a look. So again, I just choose some arbitrary value of voltages just to help us answer this question. So one thing we know is that voltage has to decrease in the direction of field. So it's now going to be decreasing to the left. So the equipotential lines which are most right are going to be highest. So here I choose 2, 1, and 3. So we start with a simple case of parallel field lines. And as we've argued in the previous slide, what that means is because they're parallel, the electric field strength is the same everywhere, which tells us that the rate of change of voltage has to be the same. So they have to be equally spaced. So let's just assume that's kind of going to be our reference point, that to go from B to A, you're going to go from 2, somewhere in the middle is going to be 1 volt and 0. Now in this case, what we see is towards the right here, the density of field lines is larger. So if a density of field lines is larger, that should tell us that the magnitude of electric field is larger, which tells us that the rate of change of voltage is larger. So what that tells us that is over here, you have to move a smaller delta R to have that same change in voltage. So here actually I start, what I'm fixing I guess here is the voltage at A. to be 0. So, okay, so let's go actually to the right, because I'm starting at 0 here. So let's say to go from 0 to 1 volt, maybe they're going a little bit closer here, but it's more or less the same distance. But then to go from 1 to 2, because the density is getting larger, you move a smaller distance. Remember, A and B are equal distance apart. So electric field is getting stronger, the rate of change of voltage is getting bigger, so it's changing more rapidly. So by the time, let's say, we get to B, we're already at 3 volts. So again, this is a bit arbitrary, but just to make a point what these density of field lines is doing. Now here, it's the opposite. They're getting less dense, weaker electric field, smaller rate of change. So here you have to move a larger distance to get to the next increment in voltage. So maybe you already passed B and 2 volts is over here. So basically the biggest change when you go from A to B, and I guess, yeah, so the reason I chose to ask specifically A to B, because that's, although it's just asking about change, but if I asked about increase, because it's increasing to the right, you see that to go from A to B, you have, you know, in this illustration, 3 volts change. Here you have 2, and here you have less than 2. So B is the one that represents the biggest change in voltage. So here again, it's a good example where, given some information of electric fields or field lines here, then we think about electric fields, and from that we can use this relationship to make conclusions about voltage. Larger density of electric field lines also implies a larger density of equipotential lines. They're closer together. Here, the equipotential lines are closer together, where the electric field lines are close together as well. Okay, so far, all we've been talking about is point charges. You know, how boring. In real life, when there's electrostatic forces and interactions, it's not just 2 charges that are sitting out there in space interacting. It could be many more, or it could be an entire object which is charged, which is actually the most common thing. But let's just take it a step at a time. So imagine now, instead of just having one source charge and then a test charge which fills that source, now we have multiple source charges. So here I chose 3. Like you could have 2 positives, 1 negative. They could be different values of charges and stuff. So now these sources, or these source charges as a whole, represent your source, and they generate voltages and electric fields. So maybe you would want to ask, because eventually you would put a test charge there, and you would want to think about, well, what force would a test charge in this position feel due to now these 3 sources? So again, these 3, they generate both voltage and electric field everywhere in space, but how do we figure out exactly these values? So it turns out that this works by kind of this basic principle of superposition, the same way we did that. We saw superposition in waves, where the amplitudes just add up. And for voltage, it's just a simple addition. So if you go back here, and you choose this point, you can figure out what's the voltage at this point due to this charge, Q1, due to Q2, Q3, and you just add up those 2 voltages, and that's going to be your net voltage due to the 3 charges. Now that's still the same with electric fields, except we're no longer adding up scalars. Electric fields are vectors. We have to be careful. So the total electric field due to some combination of source charges, it could be 3, it could be more, is the sum of vectors. So what we'll have to do is review vectors. So I know that we played quite a bit with them in 7b, but it's been a while. Now we return to them for the first time in 7c. So I will go through an example. I won't necessarily review all the aspects of vector algebra, but I'll review it through an example that I will show shortly. Okay, so let's start with a simple or simpler one-dimensional case first. So imagine here you have two charges, Q1 and Q2, and I make both of them negative. And then we want to figure out is what is the electric field somewhere over here? Not necessarily in the middle, your distance R1 from Q1, R2 from Q2. Well, first of all, we use this knowledge that electric fields point towards negative charges. So the electric field due to this charge at this point will point towards that charge. So that's one of the vectors, but there are two charges present here. Again, because this charge is on the right, the electric field would point towards it. It's a negative charge. So here's the electric field vector due to Q2. And I just happen to make this one shorter, just arbitrary. Of course, you would need to have more information to figure out which electric field is stronger. It depends both on how far you're away from that charge and also how big those two charges are. But for the sake of speaking, I decided to make the red arrow bigger than, for the sake of example, than the blue one. So if that's the case, then the total, because the red one wins, it's longer, is going to be pointing to the left. So again, we just kind of, the way you add vectors in one dimension, all you really care about is the sign, right or left, up or down. So that's all that you have to be careful about. Once you figure that out, you can add them. So you either add them if they're pointing in the same direction or subtract them if they're pointing in opposite direction. So here, this is how we would write this out. In this particular example, Q1 points to the left, and if you choose the left to be negative, that's going to have a negative sign. So what determines the sign, one common mistake that shows up here, I want to point this out now. What determines the sign of electric field is knowing that electric field points towards towards negative and away from positive charges. So for example, this one, the blue one, it's pointing to the right because this charge is negative. So the sign here is positive. So we put a positive sign. So it has nothing to do with the fact that this is a negative charge. Well, it does. That's what determines the direction. But the sign in front has nothing to do with the sign of the actual Q. The sign in front here of this vector you choose by knowing which way your electric field points. In other words, that same Q2, if you were thinking about electric field to the right of it, that electric field would point to the left because it's, again, pointing towards that negative charge. So in that case, it would be a minus sign. So basically, you make the actual Q absolute value. You don't care whether it's positive or negative. And then you put a plus or minus sign depending if your vector is pointing to the right or the left or up or down. When we talk about 1D and in 2D, it's going to get a little bit more complicated because then we need to think about X and Y components. So this is something just I'm warning you to be careful about, but once you start practicing with it, hopefully it'll make a little bit more sense. So again, Q1 pointing to the left, negative sign, Q2 pointing to the right, positive sign. You add this up. In this case, just the way this illustration I chose to be, the negative one is bigger than the positive one, so the net is negative pointing to the left. All right, now let's look at it a little bit more complicated two-dimensional case, and this is where we really need to brush up on our vector algebra. So what we're gonna ask is this. So we have these three charges A, B, and C. And what we wanna know eventually is what is the force that acts on charge C due to the presence of charges A and B. So what we're really doing is we're making charges A and B our source charges. So there are these two source charges. And then charge C is going to be our test charge. So charge C itself does not feel its own electric field. So all we need to worry about is, first, we have this location. We're going to try to figure out what is the electric field at the location of charge C due to the sources A and B. Once we know the electric field, then we just need to multiply by that charge, which is 2 coulombs, to get the force. All right, so we're going to go through this. So let's look at each electric field individually first. So there's a charge, it's a positive charge A. The electric field due to A then is going to point away from the positive charge, so it's pointing to the right at this location. We care about this location in particular because that's what we want to figure out. That's where charge C is. That's where we want to figure out what's the force that charge feels. So that's pointing to the right. Now we have a negative charge over here, and it's no longer in a straight line, so that's where we get the 2D vector algebra here, and that's going to point towards that charge because it's negative, so it's pointing that there. And this is 45 degrees because these two distances are the same. We have 1 meter here, 1 meter here, so it makes this triangle, so this is going to be 45 degrees. This is a right angle here. All right, so one way that, let's remember that we added vectors is using this tail to head method. So we take, like, let's say the red arrow, you can move it up here. So you move the tail of the red arrow to the head of the blue one, and then you connect it, and then the green one is going to be the sum. So that's kind of a geometric graphical method of adding vectors. So at least it gives us a sense that our total electric field is going to be somewhere in that direction. So that's going to be the force that charge C feels, somewhere in that direction, because charge C is positive. So it's going to feel a force in the same direction as the field. If it was negative, it would feel it in the opposite direction. But you know, this is more conceptual, you get a sense, but if we want to know exactly what is this angle, what's the magnitude of the force, we have to do algebraic vector addition. How do we do that? Well, let's look at the electric field A. That one is the easy one because it just has a component in the plus x direction. This is the magnitude of that electric field. It has no component in the y direction. Now B, we know that there is this angle 45. How do we find the x component? It's the cosine of 45, but we have to put a minus sign in front because the x component lies in the minus x direction. The y component is up, so it's positive. So it's going to be the magnitude of that vector, which we call EB, times the sine of 45 degrees. All right, how do we find now these magnitudes next? Well, we know the equation for electric field. The equation for the electric field is just K, this constant K times Q, A, because we're looking at electric field due to charge A, over R, A squared. So the distance to where you're finding the electric field from that charge. The charge is 1 coulomb, so we put 1 coulomb here. The distance is 1 meter, we square it, so it just ends up being 1 meter squared. So that's our magnitude. Of course, if you wanted to get a number, you would plug in for K. K is an ugly looking constant, so for now I'm going to carry that around. Okay, what about B? What's the magnitude? So what we need to know is we need to know the distance, the distance from charge B to this point. We can use some trick. This is 1 and 1, Pythagorean theorem. So that distance is going to be square root of 2. The charge is 2c. We're just finding magnitude here. So we don't care about the sign. When did we care about the sign? When we figured out the direction, that it points towards it. That's where the sign comes in. At this point, when we're doing the actual magnitude, we just care that its magnitude is 2c. What is the distance? The distance is square root of 2. You square it. And because it's square root of 2 squared, we get a 2. It cancels with that 2. Turns out that we get exactly the same magnitude. Doesn't have to be that way, but it works out that way in this example as EA. So we just get K 1c over 1 meter squared. Same magnitude. All right, so now just the rest is just kind of math, but let me just go through with it because again, you might be a little bit rusty on this math. So remember, we just found that the magnitudes are the same. So the magnitude of A and B is the same, which is just equal to E. I'm just setting it equal to E, defining it that way. How do we sum these vectors? We sum them by component. So there's the component of EA and EB that we found previously, but now we just write that magnitude in terms of this E. So when we add, and then the cosine of 45 is just 1 over root 2 with a minus sign there. And now we just add the x component. So we get this square root of 2 minus 1, because that's just 1, 0 over root 2. And here we get 1 over root 2. And, you know, at this point, you know, you plug in what root 2 is in the calculator. So that's what you get for your total electric field vector. And by total, it means the contribution of electric field due to charge A and B. Okay, but eventually when we're answering these questions about forces and fields, we want to always, or in general with vectors, a nicer way to represent a vector is in terms of magnitude and direction. So to find magnitude, we use this Pythagorean theorem, take the square root. Remember, E is a constant, which equals to Kc over m squared. And then how do you find the angle? It's the inverse tangent of the y component. We go back, that's the y component over the x component, 0.293. You plug that into the calculator. If we want it in degrees, end up with 67.5 degrees. And we know that it's in the first quadrant, so northeast. Okay. But we weren't asking about electric field. We were asking about what is the force. So I'm just bringing it back this picture here. What is the force this charge feels? So here's our relationship between force and electric field. So there should be a magnitude sign here as well, because now we're just thinking about magnitude of the force. So the force on charge C by the contribution of A and B, we can rewrite that as Q of charge C, that's our test charge, times the electric field of the source, so the electric field due to A and B. Q is plus 2C. So here you would put in, well, okay, so if you're talking about just magnitude, you wouldn't put the minus sign if it was negative, but direction, if this was a minus C, it would flip the direction. So instead of pointing northeast, it would point southwest if this was minus 2C. In this case, it's plus 2C, so it's going to point in the same exact direction as the electric field. And then you can calculate it, and if you plug in values of K, and I'll leave that up to you, you should get this value in newtons for this force. Where do we get that number from? So here's a slide that you should refer to if you ever need to get exact numerical numbers with some convenient units, which I haven't mentioned so much. So what is electric field? It's using this equation, it's force over Q. So a convenient unit to use is newtons over coulombs. Q has units of coulombs. And it turns out to also be this in SI units if you convert newtons to kilograms meters over second squared. And then there's some other relationships. Sometimes you see this in terms of K, the equations for Coulomb's force. Sometimes you see it in terms of this other constant epsilon naught. So I'm just kind of presenting this to you because you might see examples with these different units. Typically in 7C we use K. So K, which is 1 over 4 pi epsilon naught, equals to this big ugly number. That's why I wasn't plugging it in earlier on in the calculation. You just want to do that at the end. That's in newtons meters squared per coulomb. So then when you plug all of that in into your force equation, you should just get newtons out. All right, so I know this was a bit heavy calculation. I really suggest that you look at the slides and really try to work through this as kind of your first example of this vector addition with electric fields and forces, and kind of keeping a lot of these concepts in order, especially, what how do you deal with positive versus negative signs and things like that. And if you really don't remember vector algebra, I suggest you look back to your 7B notes where there's, you know, a couple of DLs where you really went, you know, specifically focus on just the vector part of things without seeing where it applies to physics. All right. So I think I'm getting kind of close to being done, but there's just a couple of examples I want to go through that are not your point charges, which is again much more real to applications. Normally you don't just have point charges floating out in space. And in general, you know, why do we even need these fields and so on? Well, field lines can get really complicated. So I'm just showing you an example of there are sort of 3-point charges here, and they have different strengths. So the stronger the Q is, the higher the field is, so the higher the density should be here. And then you can just, by looking at this, see that this must be a positive charge because field lines flow away from it. So is this one. That one is negative. Field lines flow towards it. So we have these 3 sources, and they create this this type of electric field. So why are they helpful? Well, once you have some source configuration, now you can take a test charge and immediately, without thinking about each time, you know, calculating your superposition and thinking about it, this gives you a good sense of how this charge will behave in this electric field. So if we put a negative test charge right here, and you want to ask which way is it going to feel a force, it's going to feel a force tangent to the field line in the opposite direction of the electric field. So see the electric field lines point in that direction, but because it's a negative charge, it's going to feel a force that way. So if that charge starts here, the force, it will move that way. Oops, going the wrong way. Now if we put, what do I say there? What about this one? Well, here we have a positive charge, so it's going to feel a force in the same direction as the field that way, but it also is going to feel a much larger force there. Why larger? Because the electric field is larger here. How do we know that the density of field line is more? So here, opposite direction electric field, but smaller magnitude. Here, same direction of electric field, larger magnitude in force. All right, let's practice a little bit this idea of superposition with a couple of clicker questions. So here in the figure below, we have a charge. Here you're given that this is +2 coulombs. And then there's some position in between these 2 charges. So we have 2 charges, this one is unknown. We choose this position A such as the distance to the +2 Coulomb charge is x, but the distance to the unknown one is 2x. And what you are given is that the field at A is 0. How is that possible? So if the field is 0, what is a possible value for the charge, for this unknown charge? So first, actually, I think the easiest thing to do here is first to decide about positive or negative. And that we'll know from direction. We know that the electric field has to cancel there. We know that this charge, which is positive, the electric field due to the positive charge points away from it. So the electric field has to point to the right due to the known charge, which means the only way that we can have an electric field that goes to 0, cancel, if that electric field points to the left. How can we have an electric field point to the left due to this charge? That charge has to be positive. Why positive? Because the field has to point away from it. So that eliminates all the negative answers. Now the rest of it is about the magnitude, and here we can use this equation. So let's write this out. So again, due to the known charge, it's pointing to the right. Its magnitude is 2c, so we put 2c for q, and the distance is x. Now this one, which we determined already, has to be positive also in order to even, oops, wrong way, consider that cancellation. And what we know, so imagine first we don't know that that's 8. What we know is that the distance is 2x, and we square that because it goes as 1 over r squared. So we get 4x squared. And we know that these magnitudes have to be equal and opposite, equal to, so they subtract and go to 0. So if this is 4x squared and this was 2x, I mean x squared here with a factor of 2, what we know is that in the numerator we have to have 8c to get this factor of 2. So what that tells us is that this charge has to be 8 coulombs. So 4 times, why? Because this is double the distance, but remember with distance you square it, so that has a contribution of being 1/4 less due to the distance, so the charge has to be 4 times as large. So this is how you kind of think about this superposition in this question. Okay, so here's another question for you. So here we have 4 charges, and we have a central point here in the middle, which is the same distance to all 4 charges. So what you're told here is that all the charges have the same magnitude. So they're the same magnitude of 1 coulomb, but some might be positive or negative, we don't know. Another thing you're given is that the net electric field is in the plus x direction, so it points to the right. So the question is, which one of these are true? So you're given some choices with A's for A, B, C, and D, either being plus or minus coulomb. So that's the choice for all of them. Maybe all of them have the same sign. Okay, so let's think about that. The fact that it's in the plus x direction tells us that there's no contribution in the y direction. So that means that, let's say if A and C were both negative, then the field would point towards A and towards C. If they were both positive, then it would be away from A and away from C. So either one would cancel the contribution in the y direction. So what that tells us is that A and C have to have the same sign. So if we look at the choices, for example, choice D would be out because A and C have different signs, and choice E would be out. So we're down to these choices. All right, so another thing, you're told that it points in the plus x direction. So what does that mean? They have the same magnitude. So it's not like, you know, the positive one can be bigger than the one pointing in the opposite direction. So that means that both the electric field contributions have to point to the right. To point to the right towards B means B has to be negative, and for D to point to the right, it means that the field has to point away from D, so D has to be positive. B negative, D positive, so your only possibility for that is choice C. They cannot have the same sign. A and C have to be the same. Here they just happen to be -1, but D has to be positive. So choice C is the correct answer. All right. Okay, I know it's a bit of a long lecture, but there's a few more things I want to get through. Okay, so far again, we've talked about 2-point charges, and we introduced a couple of more, and we saw how superposition acts. What about if you had an infinitely charged plate? So I'm not going to go into really the details of this proof, and you did this a little bit in DL, but it turns out it's a kind of a very special case, because it turns out that the electric field is constant near an infinitely charged plate, which means that, you know, we're used to thinking point charge, as you go away from the point charge, the field and the force gets weaker. That's not true. Of course, in reality, there's no such thing as an infinite charged plate. So it's about the size of the plate relative to the distances at which you are looking at the plate. So if you have a, you know, relatively large plate, but you're only a few nanometers away from that plate, for that charge, this plate might as well be infinite, if it's even only a square meter or something. So it's about relative distances. So whenever we say infinite charged plate, we're looking at that limit where the plate is much larger than the distances were from the plate. So in that limit, the electric field is constant. how do we draw a constant electric field? Well, that tells us that the lines have to be parallel. So we already kind of discussed this, but not in terms of this infinite charge plate. I also made this plate negative, so that means that the field lines are pointing towards it. If this was positive, they would still be parallel, but they would be pointing away. Remember, towards negative charges, away from positive charges. Parallel means that the density is not changing, so the electric field is constant. So from that, we can figure out our equipotential lines. And again, I've already talked about this, but that tells us, because the field is constant, the equipotential lines must be evenly spaced, because constant strength means constant rate of change. And because here we have the field lines pointing towards the right, that means that the voltage has to be decreasing towards the right or towards the negative plate. So if we start at 5, it has to decrease that way. And we just happen to set the voltage to be 0 at the plate. And this is going to be kind of an important system for us, that you'll look at a couple of examples in DL and so on, where, you know, often it might be helpful to look at what happens when the field is constant. So it's just something, it's a way to create a constant electric field, is to have this infinitely charged plate. Okay, another important system in nature is the electric dipole. So you must have heard about this in, you know, your chemistry or some biology classes. And basically what it is that, you know, we've been talking about positively and negatively charged charges. In reality, most things in nature are neutral. They're not charged. There's no net charge. But often they're not fully symmetric, in the sense that although the net charge is 0, there's sort of a positive and a negative side to your object, like a molecule, for example. So you're going to look at DL at water molecules and represent water molecules as electric dipoles. So basically, whenever we take a neutrally charged object, and if we can represent a negative or positive side, we call that an electric dipole. So here's a simple picture of one, where the positive and negative side is separated by some distance d. And we can, from that, represent an electric dipole vector, which in physics, at least, always points from the negative to a positive charge. In chemistry, sometimes they define it to point another direction, but that's just definition. So we define it to point from the center of the negative to the positive. Of course, you might not always just have, you know, one negative and one positive charge, but you might have something a little bit more complicated like this, like a whole molecule which has, you know, a negative side here next to a positive, -2q, and so on. So there's an equation that helps you then, and we won't really be using that in too many details, but that can help you figure out exactly where the dipole moment vector is. So in here, just kind of by symmetry, you see that, you know, the negative charge is stronger here than here. So it's gonna maybe start somewhere here, kind of the center of the negative, point towards the center of the positive one, so a little bit closer to the +2q. So you can always take any more complicated molecule basically and simplify it just to this dipole moment vector, as if there's just a negative charge here and a positive charge over there. This is, you know, how do we figure out the electric field lines for a dipole? So imagine now the dipole is our source. You do it the same way as for just 2-point charges. You treat them as 2-point charges, and you use principle of superposition. There's a whole DL activity where you did that. And from that, you find a bunch of vectors, electric field vectors in space. You can kind of draw your electric field lines. So they end up looking something like this, going away from positive towards negative. So away from positive towards negative. If you have a field line that starts here, then it's going to bend back down towards the negative one. Electric field gets weaker with distance, so they get more spread. The density gets smaller as you go away from the dipole. Which way does the dipole moment point is in the opposite of the electric field that the actual dipole creates. So I think that's maybe the reason why in chemistry it's reversed. It points in that direction in physics, and you'll see kind of our reason for doing that shortly. It's going to point from the negative to the positive. And the reason is right here, is that what we care about is how does a dipole behave in an external electric field. So you have your dipole moment of your molecule, and now imagine of your dipole, you put that in some external electric field. So this is an electric field created by some other charges. And what turns out is that the potential energy of this dipole is in such a way to want to line up with the electric field. So you want to think about where is the potential energy decreasing. It's decreasing in the direction of the force. So why is that? Well, the positive side, so remember we defined our dipole moment to point towards the positive. Positive side, positive charges, they feel a force towards the electric field. Negative charges against the electric field. So if there's some kind of electric field present here, imagine like pointing in that direction, the positive charge would want to kind of, it would want to line up with that electric field. So the positive charge would go towards the electric field, and negative charge away from it. So that's how you get the dipole moment lining up with the electric field. So this minus sign, so this is how the potential energy is defined, where the cosine of this angle is the angle between the electric field and the dipole moment. So when this angle is 0, cosine is 1, and that's exactly where the potential energy is the smallest. So if the force, again, points in the direction of decreasing potential energy, where is it minimal? When this theta is 0 and the electric and field and the dipole moment are lined up. So you're gonna look more deeply into this in DL, but I just wanted to point this out. These just mean it depends on the magnitude of the electric field and the dipole moment. All right, now here, so we've talked about electric fields. Now I want you to think about how the equipotential lines look like for a dipole. So what I'm asking you to do is to rank the values of voltage given this dipole present here. So we have a positive side here, negative here. Again, field lines go from positive to negative. And I'm showing you these different points here in space. And I want you to think about voltage. Where is the voltage highest versus lowest? So in value, remember voltage can be positive or negative. All right, so I think a good way to think about this, so it turns out to be B. So why is that? Is think about the central point right in the middle. And if we use superposition here, one charge is positive, one is negative. If you're right in the middle, you're the same distance away. So the R part is the same, but the charges are different, so they're gonna cancel. The voltage is gonna cancel. So right in the middle, it's gonna be 0. So if that's 0 volts, now as we go towards the negative charge, remember voltage decreases in the direction of the electric field, then the voltage is going to decrease there, and it's going to increase going towards the positive because it's in the opposite direction of the electric field. So B is going to be the smallest value because you're the closest to the negative charge. Then A, C is where it's 0, and then it kind of flips signs and becomes positive here. So if you actually, let's draw these equipotential lines, it will look something like this. So how would you draw them? Well, first of all, you know that the equipotential lines, which are the blue ones, have to be perpendicular to the electric field. So that makes sense where it should be a straight line right in the middle. And that's what we argued has to be 0. And then it has to be decreasing from 0. So it has to get more and more negative towards the negative charge. also the density of the equipotential lines has to be consistent with the density of field lines. The stronger the electric field, the bigger is the rate of change. So over here where it's the more dense, the circle should be the densest. Over here where it's least dense, the circle should be least dense. So that's why you get these kind of funny shapes for your equipotential lines. And again, when you go towards positive charges, the electric field is going away, so the voltage has to be increasing. So if this is 2, that's going to be 3, 4, and so on. So that's how you would go from seeing this more complicated electric field lines to equipotential lines. Okay, one more thing I want to cover is conductors. So they're kind of special and they behave in a special way in an electric field. So what makes a conductor is that charge can easily move within a conductor. So imagine we take this conductor, which is this yellow rectangle, and we put it in an external electric field represented by these green lines. So what happens? There are these charges that can easily move. That's what makes it a conductor. So what's going to happen is that the positive charges will feel a force towards the electric field, and negative charges away from the electric field. So the charge within the conductor is going to redistribute itself in such a way you're going to get a positively charged side on the surface here and a negatively charged side there. So what's going to happen then is there going to be an internal electric field that builds up inside the conductor in such a way that it's in the opposite direction, away from positive towards negative. So what's going to happen is that there is this internal electric field and then the external one in the opposite direction, and they're going to cancel each other. So, initially, let's say it's going to decrease until it cancel each other. Why does it have to cancel each other? Because these these charges inside the conductor will continue moving until they no longer feel a force. When will they no longer feel a force? When there's no more electric field inside. So basically, regardless of the electric field you put, these charges will rearrange themselves until there's no more electric field. So what happens is when you put a conductor in an external electric field, there's no electric field inside the conductor. So I don't know if you ever heard of this advice that, if you're out in the woods and there's lightning, a good place to hide is inside your car. Why is your car? Because your car is a big conductor. So if lightning strikes your car, it might damage your car, but you're going to be inside, okay, because you're inside this conductor, which is often known as a Faraday's cage. So a cage, meaning that it's made out of metal outside. Conductors are normally metallic, and you're protected against electric fields. So this is why when, for example, lightning strikes an airplane, it's not necessarily the end of the world, or at least you're not going to get shocked sitting inside the airplane. It's not still ideal because, the airplanes themselves might get damaged. And there's this even physicist who turned into an entertainer known as Dr. Megavolt, and he travels around and does these performances. So he built like a costume, which is a giant, or a costume which is a Faraday's cage, and he exposes himself to extremely large electric fields, and he's totally fine, specifically to just show, that this Faraday cage it works, it's true. Otherwise, he wouldn't be risking this. So if you Google if you go on YouTube and you type in Dr. Megavolt, you're going to find a lot of cool videos with him. And here's a picture of Faraday, after which Faraday's cage is named. All right, I know it's a long lecture, but last week it was on a shorter side. So hopefully this will help you catch up with a lot of this material. And this is it for today. Thank you for listening.